So let's move forward and see more types. So this was a line plot. Let's see what a scatter plot looks like. Now, I know this is a bad example, but this is also a good example because scatter plots have to be scattered, right? So that's a bad joke. But x equals to np.random.random. Again, we are revising what we have looked at in the last lecture. So we have generated our synthetic data set right now. So we have generated 1,000 data points, which are 1,000 integers between 1 to 100, and y is, 1,000 integers between 1 to 20, and we have plotted the scatter plot. So scatter plot is, again, anything goes in this bracket is always going in the format of x comma y, but the kind of plot displayed changes with what you provide after this plt dot, right? So always remember that. Suppose I don't want to use this y. Suppose I want to use this y. Y equals to x square. Now you will see my scatter plot will change. You can see the dots. Now, since there are 1,000 points, I am not able to see the exact scatter kind of scatter plot. But if I reduce the number of points, you will see that my scatter plot looks more like scatter plot. You can see 1, 2, 3, the points are scattered. Now, in the same plot, if I plot a line plot as well, you will see that the line plot passes through this, plt.plot x comma y. I might want to provide a color red. You will see that the line plot will pass through, but right now it's not a great example because the data is not sorted. So every x comma y combination is creating havoc. So that's one problem of line plot using the scatter plot, right? So that's one issue. So if we add, let's say, more points, let's see what that does. Let's say we have 100 points. Still an issue because it's randomly generated. The data is not sorted, guys. Data, the first point might be here, the second point might be here, the third point might be here. That's why the line plot will also be generated like that. First point here, then it goes here, then it comes here. But if you sort this up, the impact will change, right? So that is just something that I wanted to show you guys, right? Now, suppose I do this using, now, since we are talking about sorting, I will help you visualize that. Suppose I create a sorted array, right? np dot arrange, or let's say np dot linspace 1 to 100 and 10 points, right? Now you will see this issue will be resolved, right? So you can see whenever this is something that me and my friends, this is an error which we face a lot of times, the zigzag line error. And the solution to that is, more often than not, your data has to be sorted. Once your data is sorted, that zigzag line error will not be there. So we have seen scatter plot and the line plot together, right? Moving on, now we move toward more, statistics kind of plots. So first up is histogram and bar plot. Okay. Now this is more realistic oil and gas example. Suppose I want to generate a data set for porosities of sandstones and porosities of limestones, or let's say carbonates. And this is some data frame that I've created. Let's see this data frame, what it looks like. So the data frame is df.head. Let's see what it looks like. So yeah, so we have sandstone and we have carbonate, right? And whatever is the data inside it, it's the percentage format of porosities of both of them. Now I want to see the distribution of porosities of sandstone and porosities of carbonate. When I say distribution, what it means is I want to see in one plot, I want to see a lot of information about this univariate continuous data. Okay, porosity is a single parameter, so that makes it univariate. And I should not say variate right now, but yeah, it's a single parameter. And in one plot, I want to see where it is centered, how much it is spreading around the center, what is its peak, and all of these things. And I want to also compare it with the porosity of carbonates, let's say. It's very easy to do that in Python, and I will show you how. And this will also help you, understand the nature of distributions, right? So I should label it so that people, I'll label it, since now we know how to label. So this is for sandstone, right? And this is for carbonate. The alpha that you see is the transparency of this plot, right? If I do alpha equals to 0.9 and 0.9, you will see the nature of the plot will change. You'll see it gets dark, right? But I like it, so let's keep it that way. And plt.legend s ah, sorry. Yeah, so do that plt.legend. Brilliant. So now there is some information in front of us. We have a histogram, which is more like for every range, we are providing the frequency on the y-axis. So the sandstone porosities are centered around 25%, which is true because sandstones have a larger, they are more porous than carbonates are. So you can see the carbonate porosity is centered around 10 to 8 to 10%, right? So it's obvious that it's good. It's a good graph because it tells you that majority of the carbonate porosity distribution is lesser than the sandstone porosity distribution. That's true. Okay. Now, next thing that you can see is more and more spread is there in sandstone. So there is a lot of variability in the data for sandstone porosity. A lot of information this can tell us. What information you can like grab from this is sandstones tend to have a huge variety of porosities, right? It's not that they will be fixed around a certain. You have seen a possible porosity, maximum porosity of 47%, ideal, theoretical. But that is there, right? 50 is, since it's synthetic, it's not a correct representation, but it's obvious that sandstone porosity will be hugely spread. Carbonates also might have outliers because of fractures and other Wagi porosities, etc., which is not shown in this. But yeah, so this is the information that a distribution shows us, and histogram is more like a very layman representation of a distribution, right? And this was a good exercise to understand how to look at a distribution. More flat the curve, more is the standard deviation of this distribution. More peak the curve, like more sharp the curve is. For example, here carbonate is sharper than sandstone. That means that the standard deviation of this sample is not that great. It is more and more centered around the mean, right? Or the center, right? So that's one information. That's what standard deviation means. In this example, sandstone has a higher standard deviation in porosities than carbonates. Okay, so let's move ahead. I will come back to seaborne later on, but just because I showed this, I wanted to show it in seaborne as well. So this is how you do it. Import seaborne. It's called a KDE, called the kernel density estimator plot. So that's okay. And we will come back to it later. And we will look at the box plot also later on. But just to give you a heads up, what a box plot tells you, it's more like the same distribution. We are looking at it in a different way, but in a format of boxes. And every edge of the box, every line that you see in the box is the percentile. Okay, so the leftmost uh, box line that you see, the edge that you see, it's the 25th percentile of carbonate porosity, and the rightmost is the 75th percentile of carbonate porosity. Again, this is one box, shows you the percentiles and the outliers of a single distribution, which is carbonate porosity. Now we go to the next box, which is green box, which is the sandstone box. So you can see the sandstone box is more spread and the carbonate box is less spread. Again, reiterates the fact that carbonate porosity distribution is very, very centered around the central porosity value, right? And yeah, so this carbonate center around, it's again carbonate central porosity. Central tendency can be anything. It can be mean or it can be median, whatever you want to call it. But right now, what box plot shows you is the median, the 50th percentile. Okay, so the median porosity for carbonates is 10%. The median porosity for sandstone is 25%, or roundabouts, right? Now, this dots that you see, they are the outliers or anomalous porosities in carbonate samples. They might be coming from, let's say, very fractured or very wuggy kind of carbonates, right? So you can see, according to data-driven decision making, outliers are some things which are basically, if you want to look at it from a distribution plot, which is this one. This is, let's say, this is the mean. Whichever lies to the right or to the left of 3 standard deviations or more from the mean is called an outlier. So that's one definition of an outlier. So one standard deviation, let's say, is 10, then 10, then 10. So 30 units from 30, 25, 55. Beyond 55, whichever data is lying, it's called an outlier. Again, beyond left side as well, whichever data is lying, it's called an outlier. So that's the definition. Box plot helps you see the outliers in the dots. So for a carbonate, porosities close to 23-24% are destined as outliers for this particular example. So great discussion in depth about how to look at box plots and how to look at distribution plots.